Hello, everyone. Let's discuss training models. Specifically, we want to discuss regularized linear regression. We studied linear regression and also look at from gradient descent perspective how to solve linear regression models. On top of that, we studied polynomial regression. Polynomial regression helps us to increase the degree of polynomials. So with the hope that the model can fit the data better. However, as you know, once the model becomes more complex, we tend to decrease the bias, but the variance of the model tend to increase. As a result, we want to leverage something called regularized linear regression to regularize what we studied in linear regression with the hope that the model from linear regression can generalize much better. Let's do a quick review of what is linear regression. So linear regression is a linear model that makes a prediction by simply computing a weighted sum of the input features plus a constant called the bias term, also called the intercept term. So it's as simple as y hat equal to theta 0 plus theta 1 x1 plus theta 2 x2 all the way to theta n xn. All the thetas are parameters that we're trying to estimate, and the x are the features. Y is a predicted value. In vectorized form, it can be represented in equation 4-2, essentially y hat equal to theta dot x. Recall that we're trying to solve for theta that can minimize this quantity. This quantity is called mean squared error, MSE, which is a summation of theta xi predicted value minus actual observation squares, and sum of them together divided by m gets the average. This is our objective function and the cost function. We're trying to minimize this cost, MSE. How about a regularized linear model? One of them is called ridge regression. So ridge regression is a regularized version of linear regression. It is going to add a regularization term that is called summation of sigma I squares times alpha. This is added to the cost function, essentially added to MSE, and then this function is called L2 form just because it has sigma I squares and summation. That's L2 form. As a result, if you look at this function, objective function now becomes MSD theta plus alpha, and so a half of alpha summation of this sigma I squares. This half is really trying to just another constant that you can use. But what is alpha? Alpha is something called hyperparameter, which is something you would be able to adjust in your model. We'll discuss what exactly is alpha is and how it's going to work. One thing you should be aware here is what we're trying to do is we're hoping that by adding an extra term, in order to minimize the whole quantity, if my alpha is really big, what happens is the theta has to be small. As small almost meaning as close to 0. So if your alpha is too big, we are driving the coefficient of each feature's impact on the y close to 0. This is the important aspect. If you look at next slide, for different experiment of that alpha. For example, let's look at what's on the left-hand side. For linear regression, it's a linear model without alpha. Alpha equal to 0, essentially just regular linear model. This one would be the blue line. And then when alpha is 100, which is bigger, much bigger than 0 for sure, then you can see that the dotted red line almost shows a 0 slope. It's driving the coefficient, especially the slope, close to 0. If you look at here, because we have theta I starting from 1, right? Theta I from 1. That's why it's driving the slope close to 0 once alpha is too big. It's the same thing for the what's on the right hand side, which is polynomial regression, and then without alpha or alpha equal to 0, it's just this regular blue line, and then when alpha is even a little bit small, a little bit larger than 0, which is still small, then that's the blue line, and when alpha is 1, which is much larger than this green alpha, then you can see that it's kind of at least in this section, the slope is smaller. Okay, this is ridge regression. What turns out to be that, if you recall, in linear regression, we could have closed form solution for the theta estimate, which should be having the function form without this alpha times a, which is x transpose times x inverse times s transpose times y would be the theta estimate for linear regression. With ridge regression, that extra term in the objective function, then now the theta estimate has extra term as well, x transpose times x plus alpha a. This alpha a is unique for ridge regression comparing to regular linear regression. A is n plus 1 times n plus 1 identity matrix, and alpha is the hyperparameter that we just introduced. Specifically in scikit-learn, you could leverage a ridge class, and then ridge here use the alpha equal to 1, use a specific solver, and try to use ridge regression to fit x and y. Once the model is fit, you can predict a specific value of x. When x is 1.5, what is your corresponding estimate of the y? Or you could also use stochastic gradient descent SGD regressor with penalty equal to L2 to run ridge regression. With that being said, you probably would be wondering, what is L1? Exactly, we are going to discuss L1. L1 is something called Lassau regression. Lassau stands for least absolute shrinkage and the selection operator regression. Now the difference is, instead of sigma I squares, summation of sigma I squares, now it's summation of sigma I absolute value. We add this regularization term to the cost function with the hope that when alpha is really big, you're driving the thetas to be smaller. Of course, you have to have a balance to figure out what exactly would be the right alpha. Same story for Lasso regression based on the experiment. It's having very similar pattern as what we saw in the ridge regression. So here on the right hand side is really what's Lasso. What's on the left hand side is a ridge. Just for comparison purposes, you can see that you can leverage Lasso directly from sklearn, and then Lasso you can specify what is the alpha level. In this case, alpha is 0.1, and then you can run the regression and predict as well. That's Lasso regression in scikit-learn. Let's compare L1 penalty versus L2 penalty. If you recall, I just put them together. This is L1 penalty, that's coming from Lasso, and this is L2 penalty for ridge regression. The behavior is slightly different. So you might be thinking, for the theta 1 versus theta 2 axis, why do we have all these squares being more like a solution space, right? If you look at this function form, what should it be? It should be alpha, absolute value of theta 1 plus theta 2. Theta 1 absolute value plus theta 2 absolute value should be a square. That's exactly why it's square. In here, it shows that when you have an initial point of 1, 2, 3, 4, 4 and 0.5, theta 1 being 4 and theta 2 being 0.5, it tends to drive to the point that theta 2 becomes 0 rather quickly, and then try to figure out where is the optimal solution. So that's L2 penalty. And also as a result for Lasso regression, just because we not only have this penalty, but also have the original MSE. That's why the solution space is no longer this square, it's actually this ellipsoid type of shape. Then if you have an initial solution that's starting from here, you're kind of doing something very similar. It drives to theta 2 equal to 0 that quickly, and then it squiggly trying to figure out where is the optimal solution. In this case here, this red dot is really the optimal solution. Minimized overall cost of regularized term plus the MSE. For L2, just because it's theta 1 squared plus theta 2 squared, that's why it's a circle. It's a circle in a solution space. If this is the initial starting point, it tends to drive to the center, where is the minimal solution for L2 penalty. Same thing in ridge regression. Of course, this is no longer a circle. It could be an ellipsoid as well, and then with some initial starting point, it drives to the optimal solution rather straightforward. So that shows the behavior of Lasso versus ridge regularization. Now, once we put those two together, this is something new. We call it elastic net. We put them together, we have both terms, we add a R here. R is essentially trying to adjust how much you want to put emphasis onto ridge or Lasso, right? If R is 1, this one would be 0, so it only becomes Lasso. When R is 1, or when R is 0, then only this term is gone because R is 0, and this term is the only term for ridge regression. So in scikit-learn, you could use elastic net to define the alpha and also L1 ratio. L1 ratio in this case would be that R. Use 0.5, which would have both of the Lasso and ridge. And you can use elastic net to fit, and then once you have that fit, you can predict for a specific point what is the output of the predicted y. That's putting Lasso and ridge regression together. Now, if you think about this, right, why we are trying to have this regularized linear regression. Again, we want to avoid overfitting with the hope that by adding that extra term on the cost function, our model is not going to be it's not going to be too complicated that tend to overfit the data. But now there's a very different way to regularize regularized iterative learning algorithms, such as gradient descent, is to stop training as soon as the validation error reaches the minimum. This is called early stopping. So if you look at the chart on the right-hand side, as time goes on, your training set, the error tends to come down, and then the validation set comes down initially at one point, started increase, and point here is you could stop right here when you saw that there's a trend that the validation error is going to increase. So how exactly can you do this? From scikit-learn, it's as simple as, for example, here you're using the SGD regressor, essentially as simple as to add this extra argument to see what warm star equal to true, so that the regularized linear model would know with early stopping. It would stop once this actually is detected. Again, this is what we're trying to discuss here is regularized linear regression model with the hope that the model will not overfit our data. It's closely related to what we studied with variance and the bias trade-off. Okay, I'll stop here and thank you.